Hi. So far we talked about collecting, storing, processing and describing data. Now comes the most important aspect of a data scientist's job, which is modeling data or coming up with data models, right? So just to illustrate this, let's take the example of, say, you're dealing with some kind of patient data where you have different readings about patients. These could be like blood sugar levels, pulse rates or cholesterol levels and so on, right? So let's take one example, which is, say, blood sugar level. Let me call this X1. So in this column, I have data about the blood sugar levels of different patients, and for the sake of convenience, I'll just sort them in ascending order, right? So here are the levels, sugar levels for various patients. So you have something of this sort, and then for and then maybe some very high values. So what this data typically looks like, right? There's a lot of cluster around this region here, which is close to 115, and then you have some smaller values and then some very big values, right? So this data looks like something of this sort, right? That you have a lot of values which are close to the mean. Let's say the mean is something around 117 or 115, a lot of values clustered around that, and you have some very small values and then some very large values. Turns out that for most physical quantities or biological readings like sugar levels, cholesterol levels, if you take a large enough sample and note down their readings, they typically tend to follow a normal distribution. This is what a normal distribution looks like. Most entries or most of the mass is around the mean, and then you have a little bit of spread on both sides of the mean, right? And I could also plot this, say, the cholesterol level or the pulse rate or other such readings. Even weight and height, for example, follow this kind of distribution where most people are in a particular range, and then you could have someone who is very short, or then some people who are very tall, and same with weight also, right? Very heavy or very light and so on, right? So now this is one kind of a model about the data, that this data actually follows a normal distribution. So coming up with such models of data and then making certain inferences on top of those models is a very important part of a data scientist job. Now, why is it important for me to understand or to hypothesize that the data follows a normal distribution is something that I'll explain with the help of an example now. So here's an example, right? Suppose there's a new drug in the market for certain medical condition, maybe for cholesterol levels or sugar levels, and there's a doctor who is interested in knowing what is the effectiveness of this drug or how effective this drug is, right? Now, to do an thorough experiment for this, you need to know something known as randomized control experiments, which we'll talk about in the course. But now, for the purpose of illustration, I'm going to set up this very simply, and it will not be correct, but I'll just set it up simply so that it's easy for me to illustrate the point that I'm trying to make, right? So what you do is you take this sample of patients, so you take certain subjects, and now you are interested in administering this drug to this sample of subjects or patients that you have taken, and now you are interested in knowing whether the drug is effective or not. So this is where a data scientist steps in. She looks at the way it would be done is, before giving the treatment, you take the readings for all these patients, right? So maybe you note down the blood sugar level or the cholesterol level, whatever you're trying to treat for all these patients, and now the data scientist comes in and says, hey, I think this data follows a normal distribution. That means I can completely describe it based on the mean and variance. It's okay if you don't understand this statement right now, that a mean and variance is sufficient to describe a normal distribution. This is indeed something that we'll cover in great detail in the course. But for now, let's just assume that we know that this can be described in terms of the mean and the variance. Okay. And now she has to help us in determining whether we can be absolutely sure, and what we're looking for here is a robust argument, right? Not just a hand wavy argument. Looks like the day that most of them had a smaller blood sugar level after the treatment, and hence this drug is effective. We are looking for more robust arguments here, because this is a very, very critical application, and since the data scientist is coming up with the data model, the onus is on her to prove this effectively to us, right? So this is the model, and now you administer this drug for 30 days and for 3 months or whatever is the appropriate time, and you note down the readings again. And again, it looks like it follows a normal distribution, and then now you can see that the mean has shifted. Earlier the mean was around 150, right? And now the mean for the same patients is around 130. Now this could be one way of just figuring it out. Forget about the shape of this distribution, just look at the mean values. Okay, it looks like that for Before the treatment, the mean was 150, and after the treatment, the mean is 130. Hence, the drug is effective. Right? That's one way of concluding things, but this is a wrong way. This is not a statistically robust way of concluding things, and let me explain why. So remember, these conclusions that you're drawing are drawing from a given sample of patients. This is not all the patients who are suffering with this medical condition. It's just a small sample of those patients. Now, it could be possible for various reasons, just by random chance, it so happened there were some 5 patients here. They had some sample of 100 patients, of which there were some 5 to 10 patients for which the drug led to drastic decrements. Right? Their blood sugar level may be decreased by 30 points, 40 points, 50 points. And then for most other patients, maybe the drop was only 3 points, 5 points, and maybe for some patients it even increased. But now on average, because you had these 10 people for which it dropped by some 50 points or so on, then by on average you might see that the average has dropped. From 150 it has come down to 130, right? But without knowing about the distribution of the data or making these assumptions, you cannot robustly argue that this drug is very effective, because of the randomness possible in this small sample of data that you are looking at, right? Yeah. So now the data scientist should be able to make robust statements of the form that I am 99% sure that the drug is effective. And here I don't mean to use 99%, the phrase 99% in the way we use it in our everyday life, right? I am 99% sure that this is what is going to happen. No, here I want a statistical guarantee. That means I have to quantify something and tell you that this is going to happen with 99% guarantee, right? Now, how to do this is a subject of statistical modeling. You need to understand things like hypothesis tests, significance test, t-test, z-test, and so on. All of these are things that we'll cover in this course. And the key thing here is that you want to be able to do a robust analysis of whatever data you have. You want to come up with very simple models. Here a model is very simple, that you have a normal distribution, and based on that you want to make certain robust arguments about the data that you have. That's the key part here, and for what you require a knowledge of statistical modeling. Now, the underlying data distribution is not the only thing that you might be interested in, right? You might also be interested in learning the underlying relationships in the data, right? So now this drug has been administered, and the doctor might be interested in knowing what is the relationship between blood sugar level and the number of days of treatment. Right? Here again a data scientist steps in. She again comes up with a very simple model. She says that I think there's a linear relationship between the number of days and the blood sugar level. So what she means is that it decreases linearly with the more the number of days of treatment. Now this is a very, very simple model, and that's the cornerstone of statistical modeling, right? You come up with very, very simple models to explain the relationships between various variables in your data. And the idea to propose a simple model is that now you can do very robust statistical analysis on that. How to do it is something that we'll teach you in the course, but this is what the data scientist wants to be able to say. She should be able to say that I am 99% sure that the sugar level drops by 3 points for each day of treatment. Now this is a very, very robust statement, and a statement like this can help the doctor clearly advocate whether this drug should be used or should not be used, right? So this kind of robust analysis, what is important to understand is that this kind of robust analysis is only possible when you use very, very simple models. In fact, the model that the data scientist is using here, if I were to write it mathematically, then the model is y is equal to mx plus c, right? So x here is actually the number of days of treatment, and y is the blood sugar level, and this is a linear relation. It looks like a line, right? I'm trying to find an equation of a line. Of course, this is again something that we'll do in detail in the course, but just wanted to give you an idea of what does a model look like. This is a model. This is the relationship, a formal mathematical way of writing a relationship between two variables. It is very simple. It's not there among all the possible choices of functions. I've chosen a very simple function. I could have chosen a quadratic function, a polynomial. I could have chosen sine, tan, hypertangent. All of these functions I could have chosen, but I chose a very simple function because I want to do a robust statistical analysis of it and give these kind of guarantees, right? Whether this is the best thing to do or not is a question in itself, but this is very important in various fields where statistical guarantees are required, right? So this is something that we will do in the course. So just a quick summary of statistical modeling. What you're interested in doing is modeling underlying data distribution, modeling underlying relations in the data set, then formulating and testing hypotheses. Hypothesis in that case was that the drug is effective, or the more formal hypothesis would have been that the average blood cholesterol level before and after the drug or rather the average cholesterol level after the drug was lower than that before the drug. And now this statement, as I said, you just can't look at the numbers 150 and 130 and come at the conclusion. You need a robust statistical analysis, some statistical tools to make these statements concretely and give me certain quantifiable guarantees that I am sure about this 99% or 95% and so on. Right? That's what hypothesis testing is about. And then again, things like goodness of fit test. Right? So I came up with a model of the data that y is equal to mx plus c. How well does this model fit the data? How do I quantify that? That is something that you study in goodness of fit test. Right? So all of this is very statistically driven. It requires a lot of knowledge of statistics, and that is going to be the emphasis of this course. And again, it is very important in various regions, various domains, including sports, healthcare, agriculture, finance, and many other places. Right? So we'll talk about it in detail in this course.